So, the very last thing I'm just going to do quickly today is go through some pretty pictures that show some of the structure formation concepts that I've just been talking about. So as I said in the lectures that I just recorded on the iPad, our challenge is to go from something like the cosmic microwave background that has very tiny variations in temperature and equivalently density, and go to something like these images of galaxies that have very large scale variations from extreme vacuum to really dense cores of planets and stars. And what we have happening is we have this balance between the dynamical collapse timescale and the pressure timescale. And as long as pressure can respond more rapidly than the collapse, you actually go and get an oscillating thing rather than a gravitationally collapsed object. Obviously, a caveat is that when I talk about collapse, I don't mean that these things collapse down and make black holes. At some point, other forms of pressure take over, for example, from the heat, from fusion, or even from degeneracy pressure, or something more complicated and quantum mechanical. So things don't really collapse all the way down. Pressure kicks in at some point, but it's not the same sort of pressure that just acts through the gas. And so this is actually a diagram of what really happens. And so what you have here in the dashed line basically is what the dark matter is doing. The dark matter is just kind of collapsing all the time. And this is just showing you the change in the density. So in other words, how much variation there is in density over your overdensity to your normal region. And so what you have here is you have these regions which are collapsing, and then you enter this period up to basically when the cosmic microwave background is formed, where you have these oscillations. These are the baryon acoustic oscillations, and they oscillate forward, up and down, back and back. This is logarithmic, so this is why they're all getting closer together. And then eventually you have decoupling. That's the point at which the cosmic microwave background is formed, and then these collapse down and become progressively denser, going up to the current scale factor. So that is a sort of picture of what is happening, what I'm describing. When you apply a more complicated model or a complicated version of the simple physics that I just described, although I think the simple physics is really quite instructive. So what do we have? Well, these are some actual simulations of what's going on. So this is redshift 18.3. Remember, redshift is 1 over A, essentially, or 1 plus redshift is 1 over A. So this is a distant high redshift snapshot of the universe. This is all from a simulation. These are not real observations. Something called the Millennium simulations. Redshift 5.7. This is the sort of most distant galaxies that we've really seen and studied in any kind of detail. Sit in here. Redshift 1.4. Half this, when the universe was half its current size. And redshift 0 is today. And so you see you go from something which really is very isotropic and homogeneous down to something which is much less so at these later times. And this sort of structure that you see here at redshift 0 is what we call the cosmic web, and it basically tells you how galaxies are distributed and how the matter is distributed along. And that's just showing you where the dark matter is, and this is just a zoomed in region around a halo. So these are these dark matter halos, which is a bit like the Milky Way. So you have one very big galaxy in the middle and lots of other galaxies around. Of course, there is gravity here, so what tends to happen is that you collapse in one axis, and then you collapse in another axis, and then you collapse in the third axis. Because your density is almost always not exactly spherically symmetric. So you collapse one way first and you make a sheet, you collapse another way and you make a filament, you collapse the last way and you make a galaxy. And so what you see here is this filamentary structure that we call the cosmic web. And galaxies, unsurprisingly, form along the cosmic web. So this is the first one was the dark matter, this is now the galaxies. Again, dark matter, galaxies, they trace one another, but the dark matter is typically more diffuse, and as we've discussed, that tells you something about the nature of dark matter itself. So that's a sort of theoretical picture of the things that I've just been talking about in the course. Observationally, there are really just three things that you want to know. So there's what's the distribution of galaxies in space. So if I can compare the distribution of galaxies in space, I can compare those to the models and ask myself whether I've done a good job or not. What is the mass or the luminosity function of galaxies? So we've seen the mass function of stars. Galaxies also have a mass function or a luminosity function. that you can measure. And that tells you essentially where the massive galaxies are and where the low mass galaxies are. And then the final thing you need to know is when were they formed. And if I know those three things for every galaxy in, a substantial sample of galaxies across the universe, then I know almost everything that I need to know in order to map out structure formation. So I don't need to know everything I need to know about galaxies, but I know everything I need to know to map out structure formation. And so these are, we've already seen some of these, what the 2D or 3D positionals of galaxies in fact look like. It looks, at least qualitatively, very much like the cosmic web, so that's good. It tells us that our ideas, where we basically just feed in the physics of pressure and gravity, does a pretty good job. We have galaxy mass functions, or galaxy luminosity functions. Here, this is plotted in magnitude, so you'll have done kaleidoscopic astronomy. You'll remember that magnitudes run backwards, so bright is at the left-hand side here, and faint is on the right-hand side, so things that are very bright have absolute magnitudes of minus 23, minus 24. Things that are a bit fainter, minus 20. The Milky Way is somewhere in the middle on the so-called knee of this luminosity function. And the y-axis here just shows you how common they are. And so that tells you that galaxies are more often faint than they are bright. And again, that's completely in keeping with the ideas of what we call the hierarchical structure, that you form things starting small and you build them up because you collapse in these different ways. And therefore, this again keeps with the theoretical picture that we've seen. And the cluster mass function, I'm afraid this is now plotted in mass rather than in absolute magnitude. Perhaps that's more straightforward. This is now for galaxy clusters rather than individual galaxies, but it looks much the same. You have many low mass clusters, you have few high mass clusters, and that's again in keeping with the expectations of the structure formation that we've just discussed. Of course, to do this, you also need to know something about the distances. And so this is just showing you some spectra of galaxies. Those spectra show these narrow emission lines that you can see. So these little lines that peak up there from things like oxygen or neon or hydrogen or something like that. You can identify the redshifts of galaxies. If you identify the redshift of the galaxies and you identify their mass or their luminosity, you can use that to infer how many stars are in them and when those stars were formed. And the redshift tells you when in cosmic history you're seeing that galaxy. And if you combine that information, then you can get what's called the cosmic history of star formation. And this is what that looks like. And so it turns out today at redshift 0, we're actually in quite a quiet place. Basically, the universe is forming fewer and fewer stars today. Back at redshift 1, it was about an order of magnitude higher. It was then gradually falling, or perhaps rather flat, all the way out to redshift 6. And there's still big questions about what's going on with the very high redshift cosmic star formation history, although some things have started to show us, quite a lot of information about that. And we hope that the James Webb Space Telescope, for example, a new telescope that will be launched, originally pre-COVID next year, probably now at least a year later, will tell us much more about that. And these are some oldish distance records. And in fact, I should actually update this plot in my PowerPoint, just showing you that there are different ways you can measure redshifts. You can do it from galaxies, which is sort of the traditional way, or you can use things that are even brighter, like quasars or gamma ray bursts, to get there. If you don't know what quasars and gamma ray bursts are, that doesn't matter. They're just bright backlights that you can use to measure distances. So, the punchline from that lecture, fundamentally, is that you can understand how structure forms from individual atoms forming all the way up to galaxies with some quite simple physics. And when you take that quite simple physics and you actually put it all together into more complicated models, the observations really agree very well with the theory.